of summation pattern. That's all. That's all time dilation is. It's a Doppler effect of the radial value of your field summation patterns folded at your within you, and that the fields that make you have a finite length within a constant of the whole of time iteration. So time, so we're way down here, and the scale of time in the whole field iteration is way out. So we're way down here. You got this big finite length, which is the universe that you're working with. Now, if you go beyond that whole sum, which is faster than the iteration of the fields you're made out of, you're gonna squish, because the rest of the stuff that makes you ain't there yet. Because you can't exist outside of your length of this. But you can keep adding it because the universe keeps adding, keeps expanding. And the more you add to yourself by jumping rungs in scalar iteration, some iteration, the more of fields that, okay, if you're right here, then the field that makes you is right here. But you want to move. So you want to move. And there's only one direction we can go, and it's forward. However, due to anti-area and area, you can move forward angularly. So, and what seems to be backwards is really just the anti-portion of our universe. So, there you go. Graph here. That's X. I mean, this is X and this is Y. And then you want to move forward. See, this is, this time. So you want to move forward. Now in scale, you're going this way. That's your scale. And here, you want to see how, speed and whatnot, that's your vector. But see, when you're here, all of this down here is in the past. So you're here and down here and now here, and so and that's not moving. That's just going with the flow. You're just sitting still while that vector, you're constantly moving. So that's what hasn't been put on the graphs, other than relativity explains it as a stationary observer, but nobody's stationary, and nobody's moving. We're just riding a continuous wave of field emergence, field summation, iteration pack. What you call it? So what you're calling a packet is the whole doggone thing. It's not one frequency. It's the whole thing. You got, because you can't get the first one, because that's what is holding everything. I mean, all of is sandwiched in that. So there's no way to ascertain the value of between nothing and zero, other than a natural number, point of nothing. But at any rate, let me continue this, because y'all understand what I'm saying here, and I have to go to the computer and start. But I'm going to do that while I'm editing. See, I'm having mental fun, or going kooky, one of the two.
Divided by c squared. Let's replace the mass with the effective mass of our photon, its energy over c squared, and the energy of the photon is Planck's constant times c squared over the wavelength. I'm
going to pause this right quick, and I'm going to make sure my mic's still working. Okay, it's still working. Okay, but the light's going red, so might have to, we're only halfway through this. We're a little more than halfway through the video. So
have this thing that's full of our wonderful fundamental constants. In fact, in the exact form as the Planck length squared divided by the wavelength. And this is where I hope it gets interesting. As you pump up the energy of the photon, reducing the wavelength also reduces the regular Heisenberg uncertainty. But at the same time, this new uncertainty increases. You're still winning the uncertainty game up to a point. When the wavelength of the photon reaches exactly the Planck length, these two uncertainty terms become the same, and any further decrease in photon wavelength actually increases your measurement uncertainty due to the warping of space. So this is...
And see, that's what I was trying to explain about scale iterations. See, what he just said was that the more you shorten the wavelength, the more you shorten the, what did he say? Shucks. I don't want to misquote while I'm looking at the video.
This is one way of thinking about it. Exactly the Planck length. These two uncertainty terms become the same, and any further decrease.
Okay, see, that's momentum and position. That's exactly what I've been saying. Momentum and position. But see, that is the abstract interpretation of field waves. They're interpreting a field wave as the act of a moving wave. And that's not what a wave is. A field wave is a density of volume of some exotic material that we can never discern. So, and the only way to calculate exactly what a wave is to only utilize what a wave property is. And a wave property is one oscillation. And you can't time that oscillation and define it by an abstract unit. You have to define the wave's oscillation as the unit. So you see, the abstract notation and the abstract way of graphing a field wave is to already have a container for it to flow through. And they're calling it the vacuum, which is the space of least resistance. Now, quantum field theory is the theory of subatomic level. And how can that already be contained by something? Anything. What is that? That's what I meant by, if you're building from the roof down, you don't know how much is between the foundation and the roof. You're just constantly going down, 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 down. You keep building, you keep making new blueprints, and then you get so abstract until it's gobbledygook. You have to start from the foundation and work up and see if that comes to this. And you start with the only possible explanations. You put Occam's razor on that paper. Trim it on down, trim the fat. Simplest explanation is often and you. So, I think I'm going to stop there in the video because I think y'all understand what I'm saying, and I think they understand that what I'm trying to get across. The Superman of physics. And while I'm saying the Superman of physics, I'm going to have, hopefully I'll have a graphic, fading in and out their photos, because I'll probably just have to use one. And that one where Einstein's like, where is it? Somewhere right in here, somewhere. I hope I can point over there. I should have used a green screen here, but at any rate, the prize-winning physicist, Nobel Prize-winning physicist, the ones that haven't won yet deserve it, So, because I've pretty much watched all of them. Eddie Wu, what's up? Yeah. At any rate, I'm tripping, man. Okay, just having fun. The whole voyage has been fun. Okay, I am Kerwin Williams, and everybody in the graphic is them, and I was using PBS Spacetime, no doubt, because he comes across really well with his tutelage, and